Okay, so simplifying radicals, because we already did some of these problems, we're going to skip a couple. Right? So we did talk about if you have a square root times a square root, like in this example up here, I can multiply those two things together. So that becomes the square root of 15 times 5, which is the square root of 75. And then now it looks like the ones you did on the warm-up. If I can find a perfect square that goes into 75, then I can reduce it. If I can't find a perfect square that goes into 75, then I can't reduce it. So this would be 25 times 3. So the square root of 25 is 5. The square root of 3 stays as a radical. Okay? So numbers inside can be multiplied together. Numbers outside can also be multiplied together, like in the next example. So I have 3 times 7 is 21. And then the square root of 5 times the square root of 8 would be the square root of 40. And then if I can simplify the square root of 40 by taking a perfect square out of it, which we've done this a couple times now, so that is 4 times 10. So that becomes the square root of 4 times the square root of 10 is 2 square roots of 10. And then I still need to multiply that by 21. And it's the same process. The numbers outside can be multiplied together. So 21 times 2 is 42 square roots of 10. Right? When you're dividing, right, the square root of 13 divided by 36. When I'm dividing by a fraction, I can separate this and take the square root of the top. So square root of 13 divided by the square root of 36. Sometimes doing that will allow you to simplify, because the ultimate goal is I can't have a fraction with a radical, so I can't have the square root of a fraction, because that makes it divided by the square root of 36. Fortunately, in this instance, I do know the square root of 36 is 6, so just taking that square root allows me to simplify that. Okay. And then you have one like the next example. If I try to do the same thing, I have the square root of 27 divided by the square root of 5. The square root of 5 I don't know, so it doesn't simplify by itself. So this is the rationalize a denominator part that it's talking about. I don't want the square root of 5 to stay in the bottom of the fraction. So to rationalize it, I need to get rid of it. And I get rid of it by multiplying by itself. So I can multiply the bottom of this fraction by the square root of 5, because the square root of 5 times square root of 5 is just 5. And if I multiply the bottom of the fraction, I have to also multiply the top of the fraction by the same thing. So similar to what we did last time, where we conjugated the bottom and then multiplied top and bottom by the same thing. In this case, I don't have to conjugate because I don't have two terms in the bottom. I just have the one term. So it's not really conjugating. So multiply that. Square root of 27 times 5 would be the square root of, what is that, 135? Okay. And then if I can simplify the square root of 135, to do that work off to the side, is there a perfect square that goes into 135? You would start at 121 and work your way back. So 121 doesn't, 100 doesn't, 81 doesn't, 64 doesn't, 49 doesn't, 36 does not, 25 does not, 16 does not, 9 does. So I can do this as 9 times something. It's 15, all right? So that might take you a little bit of time to come up with that. But so 9 times 15. So that I can simplify the square root of 135 is 3 square roots of 15. So then my final answer, square root of 27 over 5 in most simple radical terms, would be 3 square roots of 15 divided by 5. Okay. If the numbers on the outside of this fraction reduce, so 3 divided by 5 can be reduced, go ahead and reduce it. This one can't. Resist the urge to say 15 divided by 5 is 3, because 15 is underneath the radical, 5 is not, so I can't combine square root of 15 and 5. Okay. Okay, and then the two examples on the bottom now directly correlate to what we did last class where we had the a plus bi and we had to conjugate and get rid of it. So the same process will work here. If I want to get rid of 5 plus the square root of 3, just multiplying by the square root of 3 is not going to be enough because that would just make it 5 square root of 3 plus 3. So it's not going to cancel anything out. So I need to multiply by the conjugate. So I need to multiply by 5 minus the square root of 3 on the bottom and on the top. Okay. On the top, you're distributing 4. So 4 times 5 is 20. 4 times negative square root of 3 is negative 4 square root of 3. And then on the bottom, if we need to work that out long way, right, do that work off to the side. I know that some stuff should cancel out because I'm still multiplying by conjugate, so I know some stuff should cancel out. So I know the first times the first is 25. The outside and the inside should cancel out. So I'm not even going to write them down because I know because they're conjugates, the O and the I part of FOIL is going to cancel. And then square root of 3 times negative square root of 3 is negative 3, so this is 22. Okay. So when you multiply an imaginary number conjugates together, you ended up with a squared plus b squared. If it's real conjugates together, it's a squared minus b squared because that negative part doesn't get canceled out by an I squared term. So similar process with conjugates, just be careful with the signs. So this ends up being 22 on the bottom. So I have 20 minus 4 square root of 3 over 22. 20 minus 4 doesn't become 16 square root of 3, so don't combine those. Those are not like terms. Can I simplify that any farther? Sometimes you can, sometimes you can't. You have to look at these numbers on the outside, and if all of them can be divided by the same thing, then I can reduce it further. So they're all even, so I can divide all those constants by 2, and that becomes 10 minus 2 square root of 3 over 11. And that is my most reduced, simplest radical terms. Okay. And then last one on here, and then we'll skip a few on the back. So I'm going to multiply by the conjugate of 2 minus the square root of 2. So that's 2 plus the square root of 2 on top and bottom. Distribute the 10 on the top, so 10 times 2 is 20. 10 times the square root of 2 is 10 square root of 2. And then on the bottom, I know the conjugates, and if I want to use the shortcut here, it's a good time to use it. So it's a squared minus b squared, so 2 squared is 4, and then square root of 2 squared is 2. So 2 minus 2, or sorry, 4 minus 2 would be 2. Okay, so I get 20 plus this 10 square root of 2 divided by 2, and same thing, I can reduce those numbers on the outside by 2. All right, so I can divide by that 2, and that becomes 10 plus 5 square root of 2 over 1, which I don't need over 1 anymore. So that would be my final answer for that. Okay. So the next part, we're finding a discriminant of a quadratic equation. You don't know what that is yet, so we need to define what is a discriminant. And that's why there's some extra space up there above the problem. Okay. And then we're going to use the discriminant within the quadratic formula. So we also need to know, or hopefully you remember the quadratic formula. What is the quadratic formula that you learned in Algebra 1? Something squared, something. There's a lot of A, B's, and C's involved, so it's x equals negative b plus or minus the square root of b squared minus 4ac. All of that divided by 2 times a. Okay. With the assumption that you're in standard form, right, that ax squared plus bx plus c equals 0. So when we get to solving here in a little bit, the first thing you're going to have to do is make sure you're equal to 0. And then you can identify A, B, and C, and then you can plug them into the quadratic formula. Okay.
Is that minus 4ac?
Yes, b squared minus 4ac, all underneath the radical. So sometimes you'll see this all kind of grouped together. And that b squared minus 4ac is actually referred to as the discriminant. So the discriminant is the part that's underneath the radical. So my discriminant is b squared minus 4ac. And it can actually tell you a lot of things about what you're anticipating happening with a quadratic. So if your discriminant is positive, right? So if I do b squared minus 4ac and I get some positive value, anything greater than 0, doesn't really matter, right? Then I'm going to have two real solutions. And this is the part that's saying find the number and type of solutions, so that's two real. If my discriminant is something negative, that means I end up in the quadratic formula taking the square root of a negative number. So now I have two non-real or two imaginary solutions. And on the rare instance that your discriminant is exactly equal to 0, then I have one real solution, and it's the double root. That's the vertexes on the x-axis that we talked about a couple classes ago. Okay. The discriminant can also tell you if something is factorable. If your discriminant is a perfect square, then you can factor it instead of using the quadratic formula. So if you're having trouble deciding, can I factor this or not, you can just check the discriminant. If the discriminant is something squared, then you know that it's factorable. That's just a little bonus piece that's not asking you for it on here, but that is another use of the discriminant. All right, so in this example, we're going to find the discriminant first, use that to describe the number and types of solutions, and then we're going to practice solving using the quadratic formula. Okay, so on the first example, 2x squared plus 5x equals 3. Remember, I have to have it equal to 0 first before I can apply the discriminant a, b, and c. So I need to subtract the 3 and make this in standard form. 2x squared plus 5x minus 3 equals 0. It doesn't really matter if you put everything on the left side or the right side. The suggestion is to make your x squared term be positive. So if the x squared is positive where it's at, leave it where it's at. If the x squared is negative, move everything to the other side. All right. So I'm going to get this equal to 0, and then I'm going to find the discriminant. So a is equal to 2, b is equal to 5, c is equal to negative 3. So if I do b squared minus 4ac, that's 5 squared minus 4 times 2 times negative 3. You need to be able to do that without a calculator, but if you're doing a bunch of these problems and you want to type that in the calculator, it's fine. All right, that would be 25. And then negative 4 times 2 is negative 8 times negative 3 is positive 24. So I get my discriminant is positive 49, which tells me two things. All right? It tells me the discriminant is positive. So then I'm anticipating having two real solutions. Right? And that's the first part this is asking you. So two real solutions. Yeah. The other part that the discriminant tells you in this particular case is because that is 49, that's a perfect square, then this is, you could solve this by factoring. The original 2x squared plus 5x minus 3 is factorable because there are factors of negative 6 that combine to be 5. Okay? We're still going to solve this by quadratic formula. And just so we have room, because we have enough examples, I'm just going to skip this example. Okay? So you have room to work it out. So I'm going to apply the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. So that's going to become x equals, b is 5, so negative 5 plus or minus the square root of, I already did b squared minus 4ac in this problem. I don't need to do it again, right? So I can just put 49 in there, because I know it's going to equal. I already did that work. You don't have to do it again. Divided by 2 times a, which was 2. So if I simplify that now, I get x equals negative 5 plus or minus. I can simplify the square root of 49. What's the square root of 49? It's 7. And then on the bottom, 2 times 2 is 4. And we said if that number after the plus or minus sign is a perfect integer, then I can find these two answers. So I have x equals negative 5 plus 7 divided by 4. And I have x equals negative 5 minus 7 divided by 4 would be my two answers. Negative 5 plus 7 is 2. 2 divided by 4 is 1/2. So there's one answer. Negative 5 minus 7 is negative 12. 12 divided by 4 is 3. So then negative 3 is my other answer. And because those answers don't have radicals in it, that's another way you know that the original problem, which we already knew because of the discriminant, is factorable. Okay, so moving on to one more example. I'm going to do the same thing, but I'm going to skip C and come to example D. All right. So the first thing I need to do is be equal to 0. My x squared term is negative, so I'm going to move this stuff to the other side, and this becomes 0 is equal to positive 7x squared. So I'm adding that to the other side. And then 3x minus 5x would be negative 2x. And then plus 4. So I'm going to find the discriminant first on this, since I know A is 7, B is negative 2, and C is 4. So I do B squared minus 4AC. That is negative 2 squared, be careful with that, minus 4 times 7 times 4. So that's 4 minus, what is that, 16 times 7 is 71, what? 142. Should probably have done that math beforehand. Okay, and then 4 minus 142 is negative 138. So that discriminant being negative, and it's not a perfect square, so I know this is not factorable. That discriminant being negative tells me I'm going to have an imaginary solution. So I have two imaginary or two non-real solutions. So that's the first part of that question where it says find the number and type of solutions. It's two imaginary solutions. And then if I actually go to find those imaginary solutions, I need quadratic formula to do that. So it's x equals negative b plus or minus the square root of b squared minus 4ac, which I, again, did that math already. So negative 138 divided by 2 times 7, which is 14. So then if I simplify that, negative negative 2 just becomes positive 2. Plus or minus, can I simplify the square root of 138? Maybe, maybe not. So I need to check that off to the side. All right. Is there a perfect square that goes into 138 on that list? 121, 100, 81, 64. Goes into 128, 49. No? Yes? No? If everything works, then all you can do to simplify that is take the negative out. So my answer is that. Okay, but you have to check and make sure that the square root doesn't actually simplify, nothing actually comes out of it. Okay? To get an answer that's in its simplest radical terms. Okay, so these steps for using the completing the square method, right? You're going to divide everything by A if A is not already equal to 1. So if A is equal to 1, you're skipping that step. If A is anything else, you're going to divide everything by A, because for the completing the square method to work, we need that A to be equal to 1. Okay? Which is why this method sometimes doesn't always work, because when you divide by A and you start creating fractions everywhere, it makes the completing the square process a little messy. So in that case, it's better to just go back to quadratic formula. Okay? But assuming we're going to use this method and we divide it by A, or we have skipped that part, right? Then you're going to move the C to the other side of the equation. And then once you do that, this third step is where this gets its name from. This is why it's called the completing the square method. You want to write the left-hand side as something squared. So you're going to take half of B and square it. And then you're going to add that to both sides of the equal sign to maintain equality. And we'll kind of do each of these steps in the first example, and I'll kind of label them as we do them. Okay. You do that step, the completing the square step, so that you can factor the left side of the equal sign, And it should always end up being factored to something squared equals a number. So you should end up in that format. And because of all the prior steps that you had done, it should be x and then plus or minus something, which we'll just talk about where that came from. Okay. And then the last part, once I get to that method, right, or that step to solve for x, I can take the square root of both sides. That's the extracting square roots method. So I can apply the extract roots method. That's just you take the square root of both sides and then solve for x. Okay. So then real quickly, so you have one or two examples to look at. Okay. First problem, x squared minus 10x plus 13. My a is already equal to 1, so I'm going to skip the first step. Right. So I'm going to skip step 1 from above. The second step is to move c to the right-hand side, so I'm going to subtract 13. So I get x squared minus 10x, and then I'm going to leave a blank for the next step. So that's step 2, is moving the 13 to the other side. And then this is the third step. I'm going to take half of b. b is negative 10. Half of that is negative 5. Negative 5 squared is positive 25. So I'm adding that to both sides. So that's step 3. Right, I did negative 10 divided by 2 squared and put it in the blank. And it has to go in both sides to maintain equality. And then step 4 is to write that left-hand side in its factored form. I know it's going to end up being something squared. That's the purpose of this method. Okay. It's always going to be x in there because I forced that a to be 1. And then the constant that's in that factor is what you squared to get 25. So I squared negative 5, so then it's going to be minus 5. If I squared positive 5, it would be plus 5. Right? So I squared negative 5, so that's always going to be half of b. So negative 5 goes there. And on the right-hand side, just simplify it. Negative 13 plus 25 is 25 minus 13 is 12. And then I solve what's there by extracting the square root, so I can take the square root of both sides. The square root of x minus 5 squared is just x minus 5. And then the square root of 12, remember we said we're solving an equation, we take a square root, that has to be plus or minus. Okay? And then I need to simplify that square root, right? Square root of 12, I could take 4 times 3, so I can take a 2 out. So 2 square roots of 3. And again, if you need to do that simplifying or radical work off to the side on the best scratch sheet of paper, something like that. All right? And then you would solve for x by just adding that 5. So I get x equals 5 plus or minus 2 square roots of 3. To solve number 2, we start the same way. A is equal to 1, so we can skip step 1. So moving to step 2, we can move this c over to the left-hand side by subtracting c. So I have x squared plus 6x plus blank is equal to negative 10 plus blank. I'm going to fill in the blank by taking half of b and squaring it. So 6 divided by 2 squared would be 3 squared. That would be 9. So I'm going to add 9 to both sides. I'm going to factor the left-hand side, and it's going to be x. And then I squared a positive 3, so plus 3. Squared is that factor. And then on the right-hand side, to simplify, negative 10 plus 9 is just negative 1. I can take the square root of both sides to solve by extracting square roots. So I have x plus 3 is equal to plus or minus the square root of negative 1, which we learned was just equal to I. And then solve for x by subtracting 3. So I get negative 3 plus or minus I is my final answer. Okay. And then on number 3, now we do have to do the first step because I have 2x squared minus 16x plus 80 is equal to 0. So my a is equal to 2. So I'm going to divide every term by 2. So that gives me x squared minus 8x plus 40 is equal to 0. And now this looks like problems number 1 and 2. So I can get the 40 to the other side by subtracting 40. So I can put a new constant on the left-hand side. So I'm going to subtract 40. And then I'm going to fill in the blank to make a perfect square trinomial. I'm going to take half of b, so negative 8 divided by 2 is negative 4. Squared is 16. So I'm going to add 16 to both sides. That allows me to factor the left-hand side to x minus 4 squared. And the right-hand side, negative 40 plus 16 would be negative 24. Extract the roots by taking the square root of both sides. The square root of x minus 4 squared is just x minus 4. And the square root of negative 24 would be plus or minus 2I squared to 6. And then I can add the 4 to the other side, so I get 4 plus or minus 2I squared root of 6 for my final answer. And then number 4 is very similar. So I could divide everything by 3 this time, because that's my A. So I get x squared minus 4x plus 48 is equal to 0. Move the 48 to make a new room for a new constant, so subtract 48 to the other side. Fill in the blank by completing the square, so take half of b and square it. Negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. Add that to both sides. Factor the left-hand side to a perfect square trinomial. It's x minus 2. And then the right-hand side would just be negative 44. Extract the roots by taking the square root of both sides. So I get x minus 2 is equal to plus or minus 2I times the square root of 11. And then solve for x by adding 2. So I get 2 plus or minus 2I times the square root of 11.